Welcome to the pre-class video on Lewis structures and formal charges, bond order, and resonance. Right, so in the last class you learned about drawing simple Lewis structures, and in this class you're going to learn about a little bit more complicated Lewis structures. Sometimes you kind of need to follow a set of rules to draw the correct Lewis structure. And we're going to use Lewis structures a lot in the next few weeks of class because they're really a useful way of looking at simple picture of bonding. Right? So for example, carbon and oxygen like to be together. They form lots of different molecules. And what I've written up here are 3 different Lewis structures of different combinations of carbon and oxygen. So here's the Lewis structure of carbon dioxide, here's carbon monoxide, and here's the carbonate anion. Right, and we can see a few things that are different about different Lewis structures. The number of bonds between 2 atoms. Well, here we have 2 bonds, here we have 3 bonds between them, here we have some 2 and some 1. Well, we can talk about the number of bonds between atoms as single bonds, double bonds, and triple bonds. Or we can talk about it in terms of bond order. What is bond order?
Good question.
I mean, it's just how many bonds there are. Bond order of 1 is the same as saying a single bond. Bond order of 2 is the same as saying a double bond. Bond order of 3, a triple bond. One of the other things we're going to learn about is, right, and so you can't predict ahead of time, is carbon-oxygen going to be a single or double or a triple bond? Because it depends on the situation. And so you need to follow the rules for some of these Lewis structures. One of the other things that we're going to figure out is that, well, even though these are both neutral molecules, you can actually build up a charge formally on the atoms within them. And it turns out that if you calculate the charges on individual atoms in these molecules, you'll come up with 0, 0, 0. So there's no charge on the molecule, there's no charge on the atoms. Right. But if you do it for this carbon monoxide, you get +1 and -1.
Whoa.
Right? Overall, the molecule is 0, and it's a covalent or a molecular molecule where they're sharing electrons, but formally you actually have a negative charge over on that side of the molecule and positive over on this side. Well, that's going to affect how this reacts. Right? Turns out carbon monoxide, one of the things it's really good at is interacting with metal ions. And one of the metals it really likes to interact with is iron. Iron in the hemoglobin in your blood. Well, what's going to be attracted to the hemoglobin in your blood, to the iron? Well, iron is a cation, it's a metal ion, and so the negative charge on carbon is going to be attracted to that. It turns out it's really attractive. Oxygen doesn't have a formal charge on either atom, and so it's not as attractive.
Sure.
Kind of weird. Another thing we're going to learn about is that I could have drawn. Is this oxygen different than that oxygen? Not inherently. Not really. And so what can we say about this location of that double bond?
Well, that double bond could be at either one of these locations, right? Like any of these could have that characteristic.
Yeah, I could have drawn this double bond down here and had a single bond up there and rearranged the electrons a little bit, or had the double bond over there. Well, it turns out in real molecules, where you have equivalent atoms, double bonds like this can move around. They resonate around the molecule. So we'll learn about that as well.
Right. So it's never in one place. It kind of jumps.
Yep. Yep. Sometimes they're pretty fixed. Sometimes they can move around. So it's kind of cool, actually.
It's exciting.
Yep. Very exciting.